Hi Charlene. Easiest way to do this, I think, is probably a video. I'll try and keep it quick. So question 7. First of all, you need to make sure that you've got the correct equations in your repertoire. So you're going to need the equation for Q, because that's the first thing you're going to need to calculate. You're then going to need this equation here, which is ultimately what the question is asking you to calculate, which is the enthalpy change. And the enthalpy change is calculated per mole, so that's going to be Q, which you're going to calculate here, divided by the number of moles present. Now, key thing to note here is that for the enthalpy of neutralisation, it's the number of moles of water that you're after, okay? And for that, sorry, this is written in kind of a bit of a weird order, but for that you're going to need this, which is the balanced equation. Now, most of the time, the mole ratio is just going to be 1:1, as it is here, unless you've got sulfuric acid, which is H2SO4, in which case you can get 2 moles of water, so just be mindful of that. Okay, and then also because at some point you're going to need to calculate moles, you need N equals C times V. So to calculate Q, we have our mass here. Our mass is going to be, for enthalpy of neutralisation, we use the total mass of the acid and the alkali combined. Now we assume a density of 1 gram per centimetre cubed, and therefore we can say centimetre cubes equals grams. So 200 cc's of nitric acid, 200 cc's of, God almighty, sodium hydroxide, and therefore that gives us a mass, total mass of 400, multiplied by the specific heat capacity, multiplied by the temperature change. That gives you your answer in joules, and then you need to convert that to kilojoules. So that's step 1, okay? Next thing to do then is to work out the number of moles of water. Now we do that by calculating the number of moles of acid or of alkali, it's the same. And because it's 1:1 ratio, that's going to be the number of moles for water. Now, I think there is a mistake in the question, because first thing to do then is calculate the volume in centimetres cubed into decimetres cubed, which is 0.2, and multiply that by the concentration, which was 2 moles per decimetre cubed, which gives you 0.4 moles. However, they have used, to get the answer that is correct, which is this, minus 57.7, they must have used 0.2 moles. So they must have said that there was 100 cc's, or that the concentration was different, whatever, it doesn't matter, but basically, and this number here, actually, if you ever get a multiple choice question on this, that is roughly around that figure between 55 and 58, or minus 55 and minus 58, is the enthalpy change associated with the enthalpy change for neutralisation for a strong acid and a strong alkali. So that is what you're looking for, but somewhere I think there's an error. But anyway, you then say 11.54 divided by the number of moles, which I think is 0.4, and they've used 0.2, and that will give you your answer. Now, you must make sure that you check your sign. Enthalpy of neutralisation is going to be negative, okay, and that's in kilojoules per mole. Right, next question, question 8. We've got a Hess cycle here. You need to calculate the formation. The answer they give, or sort of the help they give on this one, when you click on the little I next to the red cross, was bizarre. What they had along here, I've got no idea, because it had 2C in the, anyway. Oh no, in fact, I guess you've got that. Yeah, fine. Anyway, basically, what you've got is a Hess cycle, and underneath the equation I've put the elements that go into making all of these things, and then we draw our arrows going upwards, because this is enthalpy of formation. So all of these things will form all of these things, okay? So our arrows are going to point upwards. Then we can label on here with the values that you're given in the question. You're given the enthalpy change, which is minus 36.80, and then for a Hess cycle, we're going to take up, you don't have to, but to make it visually clearer, I've drawn an arrow around it. The arrow goes what's that? That's anti-clockwise, isn't it? So it goes around like that. And then we take our finger and we go, I'll do it with this finger, around like that. I'm just going to switch. I think that's what you're supposed to do, isn't it? And I consistently forget to do that to have it landscape. So you go around and trace your finger around the Hess cycle. Now, if your finger moves in the opposite direction to the arrow that you've drawn, which it's going to do for this one and this one, then that is going to be a negative value. We're going to say minus, and then those values, okay? So we would say minus 393.5. We don't know what that one is yet. As we carry on round, our fingers tracing in the same direction as these two, okay? And so that's going to be plus, okay? And so the sign for those aren't going to change. So where we're coming around here, the sign's going to change because we're moving, our fingers moving in the opposite direction to the arrows. But for this one, same direction, the sign won't change. And if we carry on going around here, our fingers moving in the opposite direction to that arrow too. So yeah, so we can then plug all of that in. So we add everything up on this side, we add everything up on this side. And Hess's law states that it does not matter which direction you go around, two sides of the triangle, so to speak, will be equal to the other side of the triangle. So if you add that and that, you'll get that. And if you add that and that, you'll get that, and so on and so forth. Okay? So with that in mind, we can say if we add these values together, we get minus 1355. So using the directional rule, tracing our finger in the same direction as these arrows, we can say minus 1355, carrying on round, opposite direction changes the sign, plus 36.80, carrying on round, we're going in the opposite direction, changes the sign, so plus 393.5, and that equals minus 924.7 kilojoules per mole. Where are we? Is that the answer? Why have I got more stuff down here? I can't remember now. Oh, okay, I think what I've done here is I've just proved basically that if you then kind of add that and that, you get that. That's it. Okay, right, question 9. No, it wasn't question 9, was it? It was question 10. So, bonds, enthalpy, bonds broken minus bonds made. Breaking bonds is endothermic, it requires energy. Making bonds is exothermic, energy is given out. And the mean bond enthalpy for different bonds does not have a sign. I think that's relevant for the next question. Yeah, okay, so for this one then we're calculating delta H, aren't we? So we need to pay attention to which bonds have been broken, including this, and which bonds have been made. So you'll notice here I've kind of broken all of the bonds with the exception of this carbon iodine one here. I've broken all of them, and I've done the same on this side, again with the exception of making that one. I've crossed out the carbon hydrogen on the broken and the made side. The reason being that you break 7 carbon hydrogen bonds and you make 7 carbon hydrogen bonds. So those values are going to be equal in their magnitude but opposite in their sign. So they're just going to cancel each other out. And the same is true of the carbon iodine bond. You break it, one of them, and you make it, one of them. Cancels each other out. So you don't need that data in order to do this calculation. You actually don't need this data either. So we break that, make and make, and we make 2 of those. So adding that and adding that, and then remembering that we say bonds broken, take away bonds made, leaves you with minus 93 kilojoules per mole. And finally, question 11. This time you're given delta H and you need to calculate the mean bond enthalpy for one of the bonds, which is, I think in this example, the carbon-chlorine bond, bearing in mind that you've got 2 of them. Okay, now this is the one where I've got a bit confused at the start of the previous question. Your mean bond enthalpies don't have a sign. You're just given the values and then you apply the sign depending on whether that bond is being broken or made, assuming of course that you have knowledge of bonds being broken being endothermic and bonds being made being exothermic. So exactly the same process, you just add up the values for all of the bonds being broken and made. You'll notice again that I've left out the carbon-hydrogen bond value because there's 1, 2, 3, 4 on this side and there's 1, 2, 3, 4 on this side, so the values will cancel each other out. So we've got over here 853 and over here we've got 348 for the bonds that we know about, but then we've also got a missing value here. Okay, so bond making, if we rearrange the equation where we say the total energy change, delta H, equals bonds broken, take away bonds made, we can rearrange that to say bond making equals the total energy change minus bond breaking. And I've kind of done that twice really. I sort of did it here and I've done it a bit more thoroughly down here. So we can say bond making, where are we? Okay, so this is delta H then. So minus 173 equals the bonds broken. Okay, so that's all of these ones. Hang on, wait, sorry. Wait, what have I done here? Okay, no, fine. Right, so bond making equals total energy change minus 173 minus bond breaking. So that's minus 853, and that gives you a value of minus 1026. Okay, so this value here, if you add this to it, then that is going to give you the total value for what's missing. Okay, and the total value is 2 times CCl bonds. Therefore, 1 ClCl, oh, sorry, that should say Cl. Therefore, 1 ClCl bond is going to be that divided by 2. Okay, I hope that helps. Bye.